Hi all, let's take a look at the remainder of the problems in section 4.4. Problems 11 and 12 are both conceptual problems looking at a graph and answering questions. There's really not much work to show in either of them. Let's go ahead and take a look at number 11 here. So we see on this curve that it looks like it's quadratic in format, and that it has a starting position of 100, has the ordered pair 2, 0, and then the ending position of 4, 100. Now this is representing, it says, the position of an ambulance in kilometers on a straight road over a period of 4 hours is given in the figure. So we would assume in this case that since the y-axis is pointing north, that initially the ambulance was 100 miles north of the home position. And then in the next 2 hours, they traveled south. And then the 2 hours after that, from 2 to 4 o'clock, they traveled backwards north, ending up at the same vertical distance from the y=0 value. Now, if it's asking questions based upon this, it says, first of all, describe the motion of the ambulance for t is equal to 0 to 2. Okay, so from 0 to 2, clearly it's moving south. It's a downward motion. So the ambulance is traveling south. Now, when we think about the first and second derivative here, remember, we could say from x=0 or t=0 to t=2, the slope is continually decreasing. So we would say its position is decreasing. Moving south is considered decreasing position in this problem. And then from 2 to 4, it would be increasing its distance from the original position of 0. So we would say it's moving forward. So south is moving backwards, north would be moving forwards. And I could also say, if I think about in terms of the second derivative, please notice this entire curve is concave up. So you say, well, what does that even mean? The fact that it's concave up tells you that your first derivative is continually increasing throughout this function. And that makes sense if you think about it. It starts off with a very negative slope, then it gets less negative as you approach 2, then it's a 0 slope, then it's a slightly positive slope, and then it gets a more and more positive slope. So yeah, of course, the first derivative continually increased. Now, let's see how that's going to impact our answers. Describe the motion of the velocity from 0 to 2. Well, clearly it's negative, it's moving down. The velocity of the ambulance from t=2, 0 to 2. Now, the velocity is increasing or decreasing. Now, automatically, you should know that, well, it's increasing. Why is it increasing? Because it's in a concave up curve. Thus, the second derivative is always positive. And when the second derivative is positive, your first derivative is increasing. Your first derivative is velocity. Well, velocity is increasing. So now the next question I love, because students would say, well, if the velocity is increasing, how could the speed be decreasing? That's where they're not understanding the difference between velocity and speed. Speed only increases if velocity and acceleration have the same sign. So I could be increasing my velocity, but slowing down my speed. So if my velocity is in a negative direction and I'm speeding it up, then I'm still going in a negative direction, but I'm going in that negative direction more slowly. So the speed is slowing down. So please remember, with speed, you say you can only speed up if the first and second derivative have the same sign. So if you have positive velocity and positive acceleration, it speeds up. If you have negative velocity and negative acceleration, it speeds up. But in this case, you have a negative velocity yet a positive acceleration. So you say, oh, that ambulance is slowing down as it gets to 2. So we say, okay, ambulance speed is decreasing, even though the velocity is increasing. And then you can say, describe the motion of the ambulance from t=2 to 4. Well, clearly it's increasing. And we would say, describe the motion of the velocity. The velocity the slopes are always positive. So you say, well, the velocity is positive. And then we say, is the velocity increasing or decreasing? Well, it's in a concave up curve. The second derivative is always positive, thus the first derivative is always increasing. So you say, yes, the velocity is increasing. Now, the question that might have surprised you in the beginning shouldn't surprise you now. You say, well, is the speed increasing or decreasing? And now the speed is increasing because your velocity is positive and your acceleration is positive. So it's speeding up or the speed is increasing. Now the next question gets even more involved than this. And please make sure as you work these, you know to scroll all the way down and answer all of the questions. Now, as a way to go ahead and think about this one, it might be best if I, let's see, try to minimize this a little bit and show you my other screen here. Yeah. So here's my thinking about this problem. I'll do that. Yeah, there we go. So this problem discusses, it says the position of a bicyclist on a straight road in kilometers is given over a 4-hour time period. And we're trying to find out, just like the last problem, whether they're traveling north or south. And again, the y-axis is north. And then whether the velocity is positive or negative, whether the velocity is increasing or decreasing, and whether it's slowing up or whether it's speeding up or slowing down over some certain intervals. Now, I've went ahead and broken this down over here, so hopefully you can make sense out of it before we scroll all the way through the many, many questions of this problem. So it's going to break it down into all of the following time intervals: 0 to 5, 0.5 to 1, 1 to 2, 2 to 3, and 3 to 4. Let's go ahead and discuss those time intervals. So if I look at the position function between 0 and a half of an hour later, well, okay, clearly the position is increasing. They're traveling north. So I could say, well, the position is increasing, which is a northward movement in this problem. Now, I know that the slope in this region, it's always positive. It starts off a very low slope. It's almost a zero slope initially, which makes sense. You start off at a slow rate and you speed up as you go. But I can see that not only is the first derivative greater than 0, because all of my slopes in there are positive, but the first derivative continually increases in that region. So it started off barely positive and got extremely positive. So I can say, well, clearly the second derivative is greater than 0 because the first derivative was increasing. Now, what about between half an hour and 1 hour? You can see, well, they're still increasing the position, but then what about the velocity? Well, the velocity is still always positive. The slope of any tangent line at a point throughout 0.5 to 1 still be positive. But then the second derivative I need you to see is is negative. Why negative? Because the first derivative is decreasing. The first derivative starts off extremely positive and it's getting less positive in this region. And now, if you were just trying to answer a question, how am I supposed to know that? If I ask you if the portion of the curve between 0.5 and 1, if I had to ask you, does that look like it could be part of a U or part of an N? And hopefully you see here that it would be the left-hand portion of an N all the way up to the top part of it. It doesn't finish out the N, of course, but if it's any portion of an N shape, you say it's concave down in that region, which means the second derivative is negative. The first derivative is losing power in that. It's getting less and less and less, even though it's still positive. Now, between 1 and 2, well, this is the first region where you see that your position function is decreasing. So I would say S is going south or decreasing in this region. And what about your first derivative? Well, the slope of any tangent line throughout this region would be 0. Not 0, would be negative. I'll get it straight in a second. So between 1 and 2, the slope of any tangent line is negative. So S prime is less than 0. What about the second derivative? Well, again, if you think about this region between 1 and 2, if I said, is that part of an N or part of a U? You'd say, well, it looks like from 0.5 to at least about 2, it's all part of it. That region is concave down. The second derivative is going to be negative. So second derivative still negative in that region. Now, what about between 2 and 3? Well, between 2 and 3, your position is still declining. So your position is decreasing. Your first derivative is still negative, but now your second derivative changed from positive to negative. How are you supposed to know that? Well, because look, the slope is decreasing more here than it is here. Even though the slope is still negative right before 3, it's not as negative, which meant at about 2, it had to start getting less negative. And so if it were going negative 10 miles an hour at 2, it's going negative 5 miles an hour at 2.5, and it's going negative 2 miles an hour at 2.8. So even though it's still decreasing, it's decreasing a lot less. So it's really, the second derivative is positive because that first derivative is increasing in that region, even though it stays negative. Now at 3, it stops being negative. And we can say, well, what about the position between 3 and 4? Well, clearly the position is going to increase pretty rapidly in that region. And the reason it increases so rapidly is because not only is our first derivative positive, since the slope is always positive, but the second derivative is positive because those positive slopes start off barely positive and they get extremely positive as you go through that. That's just telling you that your second derivative is greater than 0, which means your first derivative is getting larger and larger. So those slopes would tell us that we might have a velocity initially of about 5 miles per hour, but by the end it's going up at about a rate of maybe 20 miles per hour. So it's going more quickly because the second derivative is greater than 0. Now, let's go back in and answer their questions. So between 0 and 5, we say, well, it's going north. The velocity, well, clearly the velocity is positive. And then is the velocity increasing or decreasing in this region? Well, it's part of a curve that would be concave up. It has to be increasing. Now the speed, anytime the velocity and the acceleration have the same sign, it's increasing. So yes, your speed is increasing in that region. Now, and it might be better if I go back to the small screen here. Yeah, because it's going to ask me so many questions as I scroll down here. Notice, starts talking about between 0.5 and 1. Between 0.5 and 1, the function was still going up. So I can say that's why the bicyclist was traveling north. And then I can say the velocity is still positive because it's moving up. But then is the velocity increasing or decreasing? And we said, well, it's decreasing because it's part of a curve that's concave down. It's starting to level off. And then the speed, well, the speed is also decreasing because you have a forward velocity, yet a negative acceleration. So you say, yeah, it's slowing down in that period. For the next period between 1 and 2, and just to remind you, 1 and 2 is the first point where it started heading downward. And we can say, well, all right, between 1 and 2, the bicyclist is traveling south, S decreases. And in this region, both your first and second derivative were negative. So you have a negative velocity, and that velocity is getting more and more negative as you're going. So the way that we answer that is we say, well, the velocity is negative and the velocity is decreasing because the second derivative is negative. Now, is the speed of the bicyclist increasing or decreasing? And this is where some people would make a mistake and say, well, wait a minute, it's decreasing, isn't it? No, it's increasing. It's just increasing in a negative direction. So the speed of the bicyclist doesn't take into concern whether it's moving up or down. It's the bicyclist is moving south much more quickly in this region. So remember, the speed is increasing anytime the first and second derivative have the same sign. In this region, both the first and second derivative are negative. The bicyclist is speeding up. Between 2 and 3, you can see that's the point where he's still moving down, but he's moving down at a slower and slower rate until where he stops moving downward at 3. So we say, oh, still traveling south between 2 and 3. The velocity is negative, but then I can say the velocity is increasing because that second derivative is going to be positive. And then I can say the speed is decreasing because your first and second derivative have opposite signs. If you're moving down, but you have positive acceleration, then you're moving down at a slower and slower rate until you eventually stop, which he does stop at 3. And then between 3 and 4, this is the portion where he started going up real quickly, had north movement. The velocity was positive, and the velocity was increasing because the second derivative, the acceleration, was positive. And because the first and second derivative have the same sign, your speed is going to be increasing. Now, that's a pretty challenging problem, but fun at the same time. Now, let's look at the rest of these. All the rest of the problems in this section entail us just working out the problems. So when we look at a problem like number 13 here, we have a function given and we're supposed to find, now keep in mind here, yes, it's wanting to know your intervals of concavity like our earlier problems did, but it's throwing other things in here. We want to know any critical point that where a local minima exists, a local maxima exists. So all the questions it would have asked us in the last section, in section 4.3, it's asking now in the second derivative test. And we can use the second derivative test to answer those questions, and I'll show you that in a moment. We still also want the inflection points, and we want our intervals of concavity. When is it concave up and when is it concave down? So let's take a look at this together. When I do that here, I'll move 13 right here. There we go. So here's my original function that they gave me in this problem. It would be wise to go ahead and distribute the 13x squared and say, well, this is just going to simplify to be 13x cubed minus 143x to the second plus 12. Now, when I take my first derivative, I get 39x squared minus 286x. My second derivative gives me 78x minus 286. I know that this section, we're really just supposed to do the second derivative test, so I don't worry about the first derivative test in this. I just say, let's do the second derivative test. I set my second derivative equal to 0 to find the potential inflection points. That's going to be when 78x is equal to 286, or x equals 286 over 78. I put that into my calculator and I saw that that reduced down to a factor of, or a term of 11 over 3. Now, when I find my potential inflection point, I just go ahead and set up my first derivative test. I came back later and did my critical points. So I said, this x value will set up my second derivative test. I take the domain of the original, which is all real numbers, break it up at 11 thirds, negative infinity to 11 thirds, and then 11 thirds to infinity. I chose a test point of 0 in my first region and 5 in my second region. Now, when I plug a 0 into this second derivative, I see that I would just get a negative 286. When I plug a 5, 78 times 5, that's going to be more positive than 286, so I'll get a positive for my second derivative. This tells me that my function is concave up from 11 thirds to infinity and concave down from negative infinity to 11 thirds. Okay, so this would be all that was needed if I were just asked inflection points and concavity. But we were also asked for maximum and minimum values, and I know that they occur at critical points. So then I went back and I said, well, critical points exist where the first derivative is equal to 0. So I factored my first derivative and I had x times 39x minus 286. So that told me that I had a critical point when the first factor is equal to 0, x equals 0, or when the second factor is equal to 0. And that gave me 39x is equal to 286, which solves to 286 over 39. And that gave me a critical point at 22 over 3. Now, there is no need to go back and do the first derivative test when you've already done the second derivative test. So I know these are my critical points. They could be maxima, minima, or they could be inflection points. Now, I already know neither one of them is an inflection point because this is my only inflection point. So neither of these are inflection points, which means they either have to be a maximum or minimum. How did I know that's a maximum? How did I know that's a minimum? Well, just look. 0. Which region does it fit in? It fits in this. In fact, I used it as a test point before I even knew it was a critical point. The fact that you know you have a critical point in a region that is concave down tells you that that critical point has to be a maximum. So we have a maximum at 0. Now, what about the critical point 22/3? You say, well, 22/3 is greater than 11/3, so it's going to be in this region. What do you know about any critical point? Remember, critical point is a point where the function flattens off. Well, if the function is going to flatten off in a region that's concave down, sorry, should say concave up, then you know that that critical point has to be a minimum. So I would say since 22/3 fell in this region that's concave down, 22/3 had to be a minimum. And I tried to draw it. We know this region's concave up, x had to be your maximum. We know concave down, we know x equals 0 had to be your maximum. This region's concave up, x had to be your was your critical point of 22/3, had to be where it flattens off, has to be a minimum. So I would have went back into Achieve, entered those in for my critical point that's a maximum, critical point that's a minimum. Now it's asking us to do the same thing in number 14, but number 14 gives us a rational function. That's okay. So I went in and I said, I know I need to take the derivative twice. So since it's a quotient, I used the quotient rule. Brought the denominator up times the derivative of the numerator minus the numerator times the derivative of the denominator for the 2x there. Then I knew I was going to have an x squared minus a 2x squared. That gives me negative x squared, and I'll still have the plus 6 all over the denominator squared. Then I said, well, that's my first derivative. My second derivative, I'll say, well, all right, it's a quotient still. So I'll bring the denominator up, multiply it by the derivative of the numerator, negative 2x, minus the numerator, negative x squared plus 6. Now, times the derivative of the denominator. Any group to a power, you bring the power down in front, times the group, x squared plus 6, multiplied by the derivative of what's inside of that group. That's where the 2x came from. All of that's divided by your denominator squared, which means x squared plus 6 is raised to the 4th power down there. Now, for my second derivative, I can say, well, all right, I need to simplify this. And ooh, forgot to put my powers down there. I think what happened is I accidentally had the 4th power down here, but what I've done is I've reduced this down by a factor of x squared plus 6. So now those are to the 3rd power in the denominator. So what I did from this step to this step is I factored out an x squared plus 6 in the numerator. And then I said, well, all right, that x squared plus 6 reduces down with the denominator by 1 power. And I have my x squared plus 6 to the 3rd down there. Now, in your numerator, if this is multiplying x squared plus 6 to the 1st power, then we're going to have negative 2x cubed minus 12x. That's where that came from. Then we're subtracting. Please remember this x squared plus 6 factored out. So you're going to have 4x times negative x squared. That gave me a negative 4x cubed. And again, I'm subtracting out this group. Your next term is going to be 4x times 6, so that's plus 24x. Again, you're subtracting out all of that product. And remember, this term factored out, that's why my denominator is the 3rd power. Now it's easy to simplify my numerator. I just gather like terms, and I'll have a positive 4x cubed minus 2x cubed. That's for 2x cubed, plus positive 2x cubed. Then I'll have negative 12x minus 24x for minus 36x. Now, when I look at that denominator, even though it's the 3rd power, it can only ever be a positive number because I know x squared plus 6 is always a number that's 6 or more than 6. So I know my denominator is always positive. So then when I'm thinking, well, okay, how could that second derivative ever be equal to 0? Well, it's just when the numerator is equal to 0. So I factor my numerator, and I get 2x times x squared minus 18. And then when I'm solving that out, I can say, well, then 2x is equal to 0. I'll get x equals 0. If x squared plus 18 is equal to 0, then x squared would equal 18, and x would equal the positive and negative root of 18. Then I thought in my head, well, that's the square root of 9 times the square root of 2. That's better written as positive or negative 3 on the root of 2. Now, these are my three potential inflection points. So I go ahead and I plug them in. I can say, all right, the domain of this original function, since that denominator is guaranteed to always be positive, you don't have any vertical asymptotes in this rational function. It exists everywhere. So I say, okay, from negative infinity to infinity, it needs to be broken up with these three potential inflection points. So I say negative infinity to negative 3 on the root of 2, then negative 3 on the root of 2 to 0, then 0 to 3 on the root of 2, and then 3 on the root of 2 to infinity. 3 potential inflection points creates 4 test intervals. Now, I chose test points within each of these. Negative 10 fit in the first one, negative 1 easily in the second one, 1 in the third, and 10 in the fourth. Then what I'm trying to think of is, what do these test points do to the factored version of my second derivative? So the factored version was a numerator of 2x times x squared minus 18. And I know that that denominator, x squared plus 6, it's guaranteed to be positive no matter what I plug in. So now I start plugging things in. When I plug in the negative 10, clearly my first term would be a negative. My second term would be 100 minus 18. It's going to be a positive. I have a negative times a positive over a positive. Well, that gives me a negative. My function's concave down in that region. What about the next region? Well, negative 1 represents it. I'll still have a negative for the first factor, but now my second factor would be 1 minus 18. That's another negative. So you have your numerator is a negative times a negative. You're still dividing that by a positive. We know this is a positive. My function is going to be concave up in this region. My next region between 0 and 3 on the root of 2, I let 1 represent it. We would have a positive times a negative over a positive. Anytime you have one negative in there, the whole thing is negative. And then we know our function is going to be concave down since the second derivative is negative. In my last region, I let 10 represent it. And you can see every single factor in your problem, it's going to be a positive times a positive over a positive. My second derivative is positive, thus my original function is concave up. Now, this would be the entire second derivative test. To use the second derivative test to answer questions about maxima or minima, I would have to go down, excuse me, I would have to go down here and find my critical points. We do that by setting the first derivative equal to 0, fraction equals 0 when the numerator equals 0. So negative x squared plus 6 equals 0. All you have to do is let x squared equal 6. Then you can say, well, take the square root of both sides. X is going to equal the positive and negative root of 6. So as I'm thinking about that, I can say, well, the negative root of 6, that's going to fall in this region right here. It's not as negative as negative root of 18 or the negative 3 on the root of 2. So it's not in that first, it's in this second region. It's between negative 3 on the root of 2 and 0. Well, what do I know about any critical point that falls in a region that is concave up? Well, it has to be a minimum. So I would say I know that the critical point negative root of 6 is a minimum because it falls in a region that's concave up. What about the positive root of 6? The positive root of 6 is going to fall in this next region. What do I know about the next region? That region is concave down. Any critical point that's in a region that's concave down absolutely has to be a maximum. The only point where the first derivative is equal to 0, your critical points, it's where the graph flattens off. Well, if you're going to have a graph flatten off that's in a region of negative concavity, it's got to be a maximum because it's impossible for it to have that U-shaped. So now we say pretty gorgeous problem there. Notice all of the, oh, that's actually 13, but that one was gorgeous too. For 14 here, you can see how I answered all of the questions. Minimum at -6, maximum at 6. Our inflection points, all of the, and you have to list them out individually. -3 on the root of 2, 0, 3 on the root of 2. And then intervals where it's concave up. That was the -3 on the root of 2 to 0, union 3 on the root of 2 to infinity. And then intervals where it's concave down, and please do remember that union between your two groups, -infinity to -3 on the root of 2, union 0 to 3 on the root of 2. Now for 15. 15, now this one, it's not much of a problem. Just from using your algebraic knowledge, you should know this one. If you think about the cube root of x, the cube root of x is a graph that goes to the origin and it goes up slowly to the right, down slowly to the left. So I can say, well, what is this in relation to that function? It's just being shifted to the right 1 unit. So this is going to be moving up slowly, and then at about x equals 1, it goes up quickly, and then it really flattens off after that, but still goes up. It's going to be continuously increasing from left to right. That's just for my algebraic knowledge of it. Now, if we want to, and I do want to, if I want to bring up the calculus logic in it, it's not going to take long at all. So we say, okay, here's our original function. I'm supposed to do the second derivative test on it. So I take the derivative twice. First derivative just gives me 1/3 times the group to the -2/3. The second derivative, I'll get my -2/9 times that same group to the -5/3 power. Now, I know that this, if I rewrote it, it would be the same thing as what I have up here, -2/9 on the cube root of x minus 1 to the 5th. Well, I know that that function, it can never equal 0. -2 divided by any number in existence, it's not 0. So you just said, well, then that means that there aren't any inflection points, except, well, I should say there aren't any inflection points from the function equaling 0. There are inflection points. The inflection points in this graph occur when the first and second derivative do not exist, but the original function does exist. So whenever we get this negative fractional exponent, it's putting that factor of x minus 1 in the denominator, where initially in the original function it was in the numerator. Well, the problem with that, now we can say, well, even though that fraction can never equal 0, it could certainly be undefined. It would be undefined at x equals 1. So I can say, well, all right, that's my only critical point when the second derivative is undefined here. I go ahead and I break up the the domain of my original function at the critical point of 1, -infinity to 1, and then from 1 to infinity. I chose 0 to represent the numbers to the left of 1. I chose 2 to represent the numbers to the right of 1. Now, as I try to plug these into this function to determine what goes on, I can say, well, when I plug in when I plug in the 0, my numerator is -2. My denominator would be 9 times a negative number. So it's going to be a negative divided by a negative. I can say, well, a negative over a negative, that's going to give me a positive second derivative. And anytime my second derivative is positive, my original function is concave up. Now, when I look at the second region here between 1 and infinity, I can say, well, all right, I'm using a 2 to represent it, and my numerator, still negative. My denominator would be 9 times the cube root of 1. You say, well, that's a positive. A negative divided by a positive is a negative. So we know that region is concave down. Now I went ahead and drew this curve so you could see what's happening here. This would be the curve x minus 1 to the 1/3 power. It's always increasing, but we can see that if I ask you to break off this part right here and I said, tell me whether that's part of a U or part of an N, you'd have to say, well, it's more part of a U than it is an N. It's concave up. Now, break off the other part. From 1 to infinity, is that part of an N or part of a U? It's more part of an N than it is a U. Concave down. Gorgeousness. Then I can say, so the only thing this problem asked were critical points, were inflection points at 1, and then your intervals of concavity, negative infinity to 1 for the concave up, and 1 to infinity for the concave down. Now, please do notice, actually, it did ask questions about maxima, minima, and stuff like that. There's a lot of D and E's in this problem because there is no maximum or minimum point. So since the only critical point ended up being an inflection point, both one would both be a critical point and an inflection point in this because it makes both your first and second derivative undefined. Your only critical point's an inflection point, thus it's not a maximum or minimum. And you can see why the derivative is undefined there because the slope of the tangent line would be vertical. Now, if I look at 16 here with you, 16 gave me a polynomial function times an exponential function. So I knew I'd have to use the product rule. And Achieve told me that the domain restriction, the x values had to be greater than 0. And I actually forgot that when I first set up my second derivative test. So I had to go back and redo it here. Now, my first derivative, product rule, derivative of the first, 2x times the second, plus the first times the derivative of the second. Please remember, derivative of e to the negative x is e to the negative x times -1. Now, before I went to the second derivative, I factored this. I said, well, I could factor an e to the negative x out of both of these groups. When I do, I'll have 2x, and then this -1 is going to distribute to both of these terms. So it's going to be minus x squared plus 5. And then I went ahead and said, well, what if I want to put this in descending order and make that x squared term positive? I factored out a negative and called it negative e to the negative x times positive x squared minus 2x minus 5. But now, when I went to take the second derivative, I just used this first one, and I said, well, derivative of e to the negative x is negative e to the negative x times the second, plus the first times the derivative of the second, which I get 2 minus 2x. Again, I needed to factor. So I said, well, how about, and initially I factored out a negative e to the negative x since the first term was negative. And then I decided it was better not to factor out the negative later. But let's just say if we factor out the negative e to the negative x, then you'll have left over 2x. And if you factor out a negative e here, it's going to change this to a positive. So you say, well, it's going to be 2x plus 2x for a total of 4x in there. And then you'd still have your negative x squared term here. And then you'd be left with 5, and it would be minus 2 because you're factoring a negative out of the second term, 5 minus 2, 3. But then I realized I would rather not have my quadratic have a negative x squared term. So I factored out a negative again, made that positive e to the x times the group x squared minus 4x minus 3. Turns out it really doesn't matter whether I would have left it in this format or this format because none of the quadratics in this problem factor nicely. So I went ahead, since I knew I was going to have to find maxima, minima, and any inflection points, I just went ahead and set my first and second derivative equal to 0. My first derivative is equal to 0 when this group is equal to 0. I know the exponential function cannot equal 0. The quadratic probably could. So I set the quadratic equal to 0. I knew it wouldn't factor nicely, so I used the quadratic formula. I simplified the quadratic formula down to 2 plus or minus 2 on the root of 6 over 2. Divided 2 into the numerator, and I got 1 plus or minus the root of 6. Now, I believe this problem wants exact answers, but I wanted to get the rough decimals so I knew where they fit on the number line. So I went ahead and did those two. The 1 plus the root of 6, 3.449. The 1 minus the root of 6, negative 1.449. Now that instantly told me that, well, of course, I'm going to ignore that 1 minus the root of 6 altogether because it's not part of the domain restriction that this problem wanted us to consider. So I really only have the critical point at 1 plus the root of 6 and at 3.449. Now for my inflection points, I did the same thing. you would set this expression equal to 0. The exponential function cannot equal 0, but the quadratic can. So once again, I just said, well, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And that ended up giving me 4, and I had plus or minus the root of 28, which I called the square root of 4 times the square root of 7, and I got 2 on the root of 7. Once again, I can divide that 2 into both numbers in the numerator, and I simplified this down to 2 plus or minus the root of 7. That 2 minus the root of 7 is a negative number, so we can ignore it. And our only potential inflection point is 2 plus the root of 7, which is approximately 4.646. Okay, so now that's what I put over here. The first potential inflection point and the first critical point is below 0, so we have to ignore it due to the problem's restricted domain. So with the restricted domain and the critical points and inflection points that are relevant, I said, all right, let's do your second derivative test. We break up the domain of this problem, which starts at 0 and goes up to our first inflection point. And that first inflection point is 2 plus the root of 7, because the other one's negative. And then we go from that one inflection point on off to infinity and say, well, that's the only time this is going to possibly change concavity from 0 to infinity, is at 2 plus the root of 7. So I chose 1 to represent the numbers to the left of 2 plus the root of 7. I chose 5 to represent the numbers after 2 plus the root of 7. And it's just barely after, since 2 plus the root of 7 is roughly 4.6. Now, we plug these test points into our factored second derivative, and I'm just interested in the sign. Now, I know that e to the x, it could never equal 0, thus it did not lead to any potential inflection points. It's also not going to lead to any sign changes. No matter what you evaluate e to the x at, it's always positive. It's this quadratic that could change sign. When I plug a 1 into it, I'll have 1 minus 4 and then minus 3. Well, that's 1 minus 7. It's a negative 6. I have a positive times a negative. I know my second derivative is negative in this region. My function is concave down. Between 2 on the root of 7 and infinity, if I plug a 5 into this, of course, again, the e to the 5th is positive. That second factor would be 25 minus 20 minus 3. Well, that's a positive. Two positives create a positive product, and I know my second derivative is positive, thus my function is concave up. Now, I know that my one and only critical point was 1 plus the root of 6. It's going to fall in this region. So 1 plus the root of 6 absolutely unequivocally has to be a maximum, because it's going to be the point where it flattens off here. So I drew it down here. The only critical point in the domain is that 1 plus the root of 6. It's in the first region. Thus, you know it's a maximum. And that would finish it for this problem and this section. You'll notice on 16, it did ask all these questions that I had. This was your original function. This function over the interval that we were given had no minimum value. It had its maximum, what I was just showing, at 1 plus the root of 6. Its inflection point was at 2 plus the root of 7, concave up from 2 plus the root of 7 to infinity, and concave down from 0 up to 2 plus the root of 7. That will do it for this section. Please let me know if you have any questions.